trigonometric structure the first distribution is Mr. Akuma one out 1 year title is Dumping Buildings for Buildings Design based on sticks and the presentation this slide will
Thank you for the introduction. So as mentioned, the title of my presentation is Damping in Buildings for Window System Design Using a Stick-Slip Model. I did this research under the supervision of Professor Yuki Otamura. Totally, I have 6 chapters in my dissertation. I'll discuss why I have these 6 chapters, or even the 4 main ones, after I give the introduction. So, chapter 1, introduction. Why are we studying damping? So, what is the importance of damping in window system design? So many have said that damping is said to be one of the most important parameters in wind engineering, and particularly window system design, for example, of buildings. And I believe one of the reasons why is because there is high uncertainty in damping, which leads to lower design reliability. So, for example, I looked at different studies that took a look at uncertainties in wind loading parameters, and basically damping is associated with the highest coefficients of variation, so as high as 100%, whereas other wind loading parameters are associated with COVs only as high as 50%. And of course, many people have already studied damping. For example, the early damping models were predicated upon the equivalent viscous damping concept pioneered by Jacobson back in 1930. So it's rather simple. For example, if we have a force displacement relationship, let's say of the structure or certain parts of the structure, such as this red line, at a certain amplitude x, under cyclic motion, a loop will be formed. It's called the hysteresis loop. And then we take the area of that loop as well as the area of a triangle underneath the second stiffness or second modulus up to that point corresponding to the amplitude. Take a ratio of area. It's very simple geometry. So, and then after you've done that, so these represent, of course, work done and energy output. And after you establish the areas, we can get an equivalent viscous damping. But I think there's some misunderstanding about this concept, because I think it created an impression that damping is constant with amplitude. So the early damping predictor models assumed constant damping, and effectively they assumed viscous damping in structures. But the truth is about this equivalent viscous damping concept, it's actually associated with a certain amplitude. So let's say it's shown here in this equation. If you vary the amplitude, the damping value that you get also changes. And also it should be applied to the force displacement relationship of the whole structure. So here I talked about force displacement relationship. Sometimes only parts of the structure are used, but the whole structure force displacement relationship should be used. So that's the basis of early damping predictor models. But newer damping predictor models, such as those that we use now, are basically, they attribute damping to what is called stick-slip mechanism. So these are some of the references that talk about damping associated with stick-slip mechanism, which could occur at, let's say, contact surfaces between main structural members or between primary and secondary members. It could also occur, as Jerry said, at internal friction surfaces at the material level, or for example at micro cracks, even for steel and concrete, basically microscopic cracks. But so these current models basically just attributed damping to stick-slip mechanism. But effectively, the models themselves are based on databases of buildings in specific geographic locations. They're based on empirical data. They're not based on a study of stick-slip mechanism itself. But one good thing, one big improvement about these current damping predictor models is they recognize damping amplitude dependency, that damping changes with amplitude. These current models are of this general form. So let's say structural damping is a sum of what I call baseline damping. It's basically non-amplitude dependent or constant component plus an amplitude dependent component due to the stick slip, supposedly due to stick slipping surfaces. And then usually there's a maximum value as well. And then that amplitude dependent component, of course, a function of amplitude x and a certain coefficient, sometimes a certain power or exponent. So in visually, it looks like these equations look like this. There's a baseline damping up to a certain low amplitude point, and then damping starts to increase with amplitude. And at a certain point, the damping stops increasing and maintains a constant maximum value at higher amplitudes. And of course, for wind-resistant design, we're concerned only up to the linear elastic limit of the structure. Now, the models, they did discuss stick-slip damping models. For example, Wyatt and Davenport and Hill-Carroll use this model to describe stick-slip damping. So there's a friction. So there's a basic component or basic structure, mass stiffness, let's say dash pot. There's the stick-slip part is the friction surface plus a secondary component defined by a certain stiffness K naught. And then they associated the force displacement of this part, combined part, as so. So it looks like an elastoplastic, similar to elastoplastic force displacement relationship. But Davenport and Hill-Carroll and Professor Tamura talked about that in actual structures there's a large number of stick-slip components. So in fact, for each stick-slip component, their contributions are additive, and effectively it will cause a certain similar to, let's say, viscous damping hysteresis. I should also mention, so this is the model I showed you earlier. Lagomarsino, 1993, actually studied stick-slip models. But you can see here, just look, so these are some of this 2DOF model and the linear structure model with multiple stick-slip components. But essentially, let's just look at this 1DOF model. You can see how different it is from the modeling by Wyatt and Davenport and Hill-Carroll. So in a sense, it was good that Lagomarsino started to study stick-slip modeling, but I think the model he used was not representative of actual conditions. Now, here's the primary issue in these current damping predictor models. So this is basically the current damping models for wind-resistant design are based on measurements, damping measurements at generally very low amplitudes, compared to, let's say, wind-resistant design level amplitudes, so at higher amplitudes. So meanwhile, these models, so as I said, they assume that damping increases with amplitude and then stays maybe at the maximum value, and so on. But the problem is, well, at least some recent damping measurements showed that damping could actually decrease with amplitude. So the question is, so because they said these models are said to be based or attributed to stick-slip mechanism. So the question is, can stick-slip mechanism really define damping in actual buildings? And it's specifically for, let's say, for wind-resistant design purposes. Of course, this part we're not interested in right now. So just a few examples. Here I showed 4 plots, basically amplitude versus damping, amplitude damping, and so on. The black points are the damping data at a certain amplitude. And here you can see, and then I superimpose, let's say, the shape of the current model, general model over them. So it looks like the current models are, anyway, they're appropriate, at least for these measurements. But in fact, here actually I hid a little part, well, not a little part, but a significant part of the measurements at higher amplitudes. Here you can see that damping could decrease with amplitude. Here as well, we can see that. In fact, here there's a suggestion of maybe damping is also starting to decrease already with amplitude. So in that sense, and maybe most significantly in this example, the current model assumes maximum damping constant up to higher amplitudes, but the measurements show otherwise. So that's a question on the current models. So again, just to summarize that part, how is the primary issues we need to address? How is damping characterized by a stick-slip model? So how do we properly model stick-slip damping? And how can we consider multiple stick-slip components in actual buildings with unknown parameters? And then, so this is like a theoretical part. And then after studying that, can a stick-slip model really describe structural damping in actual buildings? Of course, for window system design, we're concerned within the linear elastic limit of the main structure. In that sense, these define the two main objectives of my study, and that's why, after the introduction, I'll present four chapters divided into two parts. The first part corresponds essentially to a theoretical study of stick-slip mechanism itself. The second part is application to actual physical structures. So I'll discuss, of course, all of that in detail. So chapter 2, I start with a very simple model, 1 degree of freedom system with one stick-slip component. So just to talk about what we are trying to model. So let's say we have a very simple 1 DOF system. It looks like frame structure, rigid mass, stiffness, and maybe damping coefficient, which could of course be set to 0. I just put it here for generality. If we introduce a secondary component, but there's no contact surface, so the system equation for this is basically the same as this. But if there's contact between the secondary component, so there's friction forces developed there, particularly when the mass starts to move. Essentially when the amplitude is very low, such that, let's say, the displacement is less than what I call slip trigger displacement, which is QC, which is maximum friction force, equal to coefficient friction times normal force, divided by K naught, the stiffness of the secondary component. So the friction force will vary linearly, basically, with the amplitude if x is less than dc. And then, but when the amplitude or displacement is greater than the slip trigger displacement, slipping starts to occur here, and then the friction force remains constant. And what happens is here, essentially, there's what is called stuck friction. So the surface does not move, while here there's slipping already at the surface. Thus, we have a stick-slip system or stick-slip mechanism occurring. And then essentially these are two, the same model at different amplitudes. So let's say I have these system equations for these two. To combine them, more simply, we can combine the system equation for the two, but essentially it's a nonlinear problem. And then I just use Heaviside step function to make it simpler. So it's a nonlinear problem. The question is, how do we get damping due to the stick-slip mechanism there? So in terms of 1 DOF mass spring dash up modeling, so this is the basic structure, and this is the basic structure with the stick-slip component. So basically this is the same model as Wyatt and Davenport and Hill-Carroll used. And they said, so this part can be defined with this force displacement relationship. So, but well, for simplicity, just I just replaced that part with one component, and this component again still has this force displacement relationship, and this component this is what I call stick-slip component. So yeah. It's basically a combination again of secondary components with a certain stiffness and friction surfaces. So at first we did not know where to start, but as I said, it's a nonlinear problem. So at first I did nonlinear analysis with the objective of observing damping out this dependency due to one stick-slip component to serve as basis for validating derived theoretical expressions. So I have a 1UF numerical model. I assigned these values, but actually they're not very important. But I subjected them to a very large equals to generate free vibration response. And very basic, I got logarithmic decrement for each cycle to get damping ratio, and of course associate that with initial amplitude of the cycle. I did a total of, I did these nonlinear analysis cases. One case, of course, without the stick-slip component first, but effectively, of course, this is linear. Essentially, it's a linear analysis. But the other 10 cases are, I just changed the parameters in the stick-slip, basically the stick-slip parameters as well as the damping and frequency of the basic structure. So to do parametric analysis. And these are the general result. So without the stick-slip component, of course, we have constant damping, constant natural frequency with amplitude. But with the stick-slip component here, we can observe an increase of damping and then a decrease. With the stick-slip component, the frequency starts from a higher level and then drops back down to the level of the basic structure only. So that's what stick-slip components can do in a system. And part of the analysis is I found that here, for example, I kept constant EC, trigger displacement, and changed the stiffness. And you can see that the damping level increased as I increased the stiffness. Here on the right, I kept the stiffness of the K0, stick-slip component stiffness, and changed the DC. And here, basically, the point at which damping starts to increase changes, and in fact is equal to DC. Here, I kept the constant friction force, K0 DC constant, but it's difficult to establish a clear relationship between the damping and the QC itself. And it would seem that the more important parameters are K0, which affects damping level, and DC, which affects the amplitude dependency effect. And so I also changed the frequency of the basic system, first by increasing mass. The blue dots are the basic system, 9.8 Hertz. When I decrease the frequency by increasing mass, you can see there's no change in the damping due to the stick-slip component. But when I decrease the stiffness to decrease the frequency, you can see there's an increase in the damping due to the stick-slip component. So stiffness of the main structure has an effect. But the damping of the main structure, basic structure, actually doesn't have an effect. So here I changed it from 0.3% to 1%. So in summary, this is just to summarize that. Again, damping level, and in fact the maximum particularly, is proportional to the stiffness ratio of the stick-slip stiffness and the main structure stiffness. And in this case, it occurs at around 2 times the trigger displacement. And of course, the damping starts to increase at exactly the trigger displacement. So now I started to derive the theoretical expressions. First, I just talked about other modeling approaches. As I already mentioned, the Lago-Marcinus model seems very different from the model we're using, and from that suggested first by Wyatt and Davenport and Hill-Carroll. In fact, even in terms of system equation, it's very different, so we will not consider that. Now, effectively, I applied the equivalent viscous damping concept. Let's say first on the friction element only, so because it's actually the only nonlinear part. And then I applied it on nonlinear stick-slip component only, as defined by, let's say, Wyatt and Davenport and Hill-Carroll. And then I applied it on the total or the whole structure. And here you can see, if we just consider the friction element only, damping with respect to amplitude just continues to decrease. If we consider only the nonlinear stick-slip component, damping just continues to increase with amplitude. But if we consider the total system, then we can get this shape where damping increases and then decreases with amplitude. So in a sense, that's the proper approach, using the total system's force displacement relationship. And again, that all boils down to using the equivalent viscous damping concept properly, applying it properly. And now this is the final derived equation that I arrived at. And again, you can see, so damping, amplitude-dependent damping is a function of, we can say, two parameters. One is a stiffness ratio, one is an amplitude ratio. So again, yeah. So the maximum value, as I also mentioned, is a function of only the stiffness ratio, or basically, yeah, damping levels. Now, as a validation, I compared with numerical results. And you can see very good match, although not perfect, between the numerical results and using my that derived equation. So, and then just one last note. I've been talking about damping with respect to displacement amplitude. In actual buildings, we usually measure acceleration or velocity. But here I showed, let's say, stick-slip displacement, stick-slip damping, let's say for a system with very low maximum damping and a system with very high maximum damping. And here you can see there's practically almost no difference between when the damping is very low and not so big difference when the damping is very, very high. So, for actual structures with damping generally below 5%, damping amplitude dependency due to stick-slip components would be similar, but their amplitude was expressed as displacement, velocity, or accelerator. So we can use those findings I mentioned earlier to other data. So again, to summarize, we needed to apply the equivalent viscous damping concept properly, the hysteresis of the total system, not just the nonlinear stick-slip component. And stick-slip damping can be characterized by two parameters, a stiffness parameter and the amplitude parameter. Chapter 3. So that was chapter 2 was very simple, one DOF with one stick-slip component. Now we talk about more realistic models of actual structures with a number of stick-slip components. And so, as I mentioned, actual buildings are likely to have much more than one stick-slip component, and actual buildings are not one DOF structures, they're multi-degree of freedom systems. So first, we do the same thing. We derive and validate the theoretical expression. We should also consider different probability distributions. And then I will do another parametric analysis using different sets of parameters. And finally, I'll talk briefly about damping in multi-degree of freedom systems with stick-slip components. So our principal model would be like this. We can express the number of stick-slip components, n number of stick-slip components, as basically a summation of stiffnesses, because there are essentially springs in parallel. So we can do a summation, and we introduce, of course, this subscript I, then the n to denote the number of stick-slip components. For now, we assume that the damping contribution from each stick-slip component is just additive. So likewise, for each stick-slip component, we just sum their contribution. So we can just use the formula we used earlier, except now, of course, we introduce the subscript I to denote each stick-slip component. And essentially, that assumption is valid, as I showed you here, comparing some numerical results with the results using that equation. So it's not a very perfect match, but I think it has to do with some errors in the nonlinear numerical analysis. But overall, looking at the shape, so there's a pretty good match. Therefore validating our equation. So now, I did a parametric analysis, as I said, because it's difficult to establish the stick-slip parameters in actual structures, especially the trigger displacement, which is a function of friction forces, which is a function of coefficient of friction and normal force. Coefficient of friction is established already in literature, but normal force is difficult to measure at different parts of an actual building. And at the same time, there's a large number of parameters, unknown parameters. So, for example, if we have 10,000 stick-slip surfaces, we would have 20,000 parameters that we need to determine. And at the same time, actually, we don't know the real number of stick-slip components in actual buildings. And at the same time, we don't know their probability distributions and coefficients of variations, so that's difficulty. So the objective for this parametric analysis is to observe various damping amplitude dependencies for different probability distributions and numbers of stick-slip components. Now there are, basically this can be done in different ways using numerical results or theoretical, but of course basically numerical analysis takes a long time, and so what I just did was, of course I used the derived theoretical expression I showed you earlier, but I also used, well, I just call them theoretically generated random numbers, but these are not, in a way they're not random anymore, but basically they are a set of numbers following a specific probability distribution of a certain mean and coefficient of variation. The good thing about using this is the results for the same distribution are consistent, whereas if we use numerically generated random numbers, they differ every run. So that could affect the results. And then, so essentially, I derived inverse cumulative distribution functions for 5 specific probability distributions. So I selected 5 with different shapes, and I validated them against numerically generated random numbers. And here they are. So again, red lines are theoretically generated, what I call theoretically generated. Blue plots are numerically generated, and you can see there's good agreement again. And this is the 5th one I used, gamma distribution with a certain set of parameters. So I selected these 5 distributions because you can see they have very different shapes. Let's say looking at the distribution functions. For example, of course, normal, Weibull, log normal are bell-shaped, but let's say uniform and normal have 0 skew and so on. So these positive skew, negative skew, and then of course the gamma distribution results in very different distribution altogether. So we're doing this because again we do not know the actual probability distributions of stick-slip components in structures, in buildings. I did a total of 672 cases varying n number of parameters, or number of stick-slip components. So I used those 5 different distributions. I varied the coefficient of variation where possible, but in fact, 200% and 500% COV can only be done when using log normal distribution. And then I also changed the relationship between the 2 main parameters corresponding to, let's say, either 0%, no correlation, negative correlation, or positive, or almost perfect correlation. And just to add, I did the quantivariate normal distribution and with using different correlation coefficients between the parameters. Because here we only have 0%, 1, or 0, 1, or negative 1, or close to negative 1 correlation. So here we can vary the correlation between the 2 parameters. And I just wanted to mention here that I had some similar properties for all cases. So there's a similarity, so we can compare. There's a point of comparison for all the cases. Here's one sample result where I might have a very large coefficient of variation for the stiffness parameter, but 0 variation for the trigger displacement. So you can see these are the parameters: trigger displacement and stick-slip stiffness. And what happens is the result resembles that of a 1 DOF plus 1 stick-slip component system. Regardless of n, here in this case I have 10,000, regardless of distribution and variability of k naught I. So even if we change these, we would have, if we have 0 variability in DCI, we would have 1 DOF plus 1 stick-slip component system. And actually, 97 out of those 672 cases have resulted in this kind of damping amplitude dependency. Now, when there's some very small variation in the DCI, or trigger displacement, let's say 5%, 10%, 10% again, and then 25%, The shape is different, but still very similar to a 1DOF system. Again, regardless of n probability distribution and variability of the stiffness parameter. So, but conversely, for all these cases, we can say that the very simple system I analyzed earlier, I showed you earlier, 1DOF plus one stick-slip component can represent an actual building with low variability in the trigger displacement. So, we can use that. But here's a little bit of a curious case. I have very high COP, 500%. Again, this is only possible for log normal distribution. But the shape is also similar to a 1DOF plus one stick-slip component system. And one explanation for that is there's a concentration. So this is for 100. There's a concentration of the sticks trigger displacement at around one small amplitude range. This is another case with n equals 1,000. Again, COV is 500%. There's again another concentration here. And this is n equals 10,000. Again, COV is 500%. And you can see there's a concentration of trigger displacements at a very narrow amplitude range, resulting in, again, damping amplitude dependency similar to 1DOF plus one stick-slip component system. This only happens when the COV is very large, so 500%. And again, it happens only under log normal distribution. And here are some more interesting cases. You can see here, DC1, which is the lowest slip trigger displacement, where the damping starts to increase with amplitude. So it started to increase there, but it only significantly increased after a while at higher amplitude. So these are some different examples with that kind of phenomenon. Here is a little bit more more delayed case, basically, and even more extreme case, and perhaps it is the most extreme. So the first stick-slip component increased damping here, but the increase in the damping only significantly increased after 3 orders of magnitude of the amplitude. So there's those kinds of cases. But so I mean, in this regard, I wanted to define another one quantity. I call it XL, where so if DC1 is when damping starts to increase with amplitude, XL is when damping starts to significantly increase in amplitude. So I'll be using that just to describe a few plots later on. In terms of number of peaks, basically 654, or most of the cases resulted in just one peak. So if you have 6 components, it's more likely to result in just one peak or one maximum damping. And then 18, there are 18 other cases, 15 cases with generally we can say 2 peaks. For example, here, damping increased with amplitude, and then reach a peak, decreased, and then reach another peak, and so on. So this is seemingly 2 peaks. It occurred for 15 cases only. This seems like it has 3 peaks, 1, maybe you could say 4 as well, and then another peak there, another peak there. What these results show us is that if we have measurements of damping only for a certain amplitude range, we do not know what's going to happen at other amplitudes. The damping would increase, the damping might continue to decrease, or it would increase again. So it's quite important to have damping measurements for a wide amplitude range. And then this is just one result out of the 672 cases I analyzed where there's no clear peak. So it seems like from here, damping starts to increase with amplitude, and then from here up to here, it seems that damping is practically constant. So that what this tells us is current damping predictor models can still be valid. So as I showed you earlier, this is the shape of current models, but we can say maybe they're valid only for a specific amplitude range. So in this sense, let's say up to here, current models are valid, but maybe beyond that point, the current model is not valid. I'll skip that one now just to show you some comparisons. So again, these are the previous ones, previous examples I showed earlier. And here you can see how the stick-slip models can be fitted into these actual full-scale damping data. And just to compare, again, you can see when the current model is used, it cannot account for the decrease in amplitude compared to, let's say, the stick-slip model to the right. And again, most significant, most visible here. Here again, it's difficult, I did not show it, but basically the stick-slip damping suggests that damping is already decreasing up to higher amplitude ranges. But current models cannot, do not use that kind of model. Now just a short note about MDUF systems. I found that in multi-degree of freedom systems, damping contributions from individual stick-slip components depend on the location of the stick-slip component and on the overall structure's mode shape. And that in buildings with more degrees of freedom, stick-slip damping contributions are reduced. But we should note that, of course, in taller buildings, there are also more stick-slip components. And in fact, so I studied, let's say, 1-story building, 2-story, 3-story, 5-story, and then I just jumped to a 50-story building, where for each floor I have one stick-slip component. And here you can see the shapes are very similar. The maximum damping within 10% of each other. But in fact, these same plots, so plotted against tip displacement at the top of the building. But if we plot in terms of tip drift ratio, the shapes become even much more similar, as you can see here. And in that sense, it's good to express damping in buildings in terms of tip drift ratio instead of absolute amplitudes. Now here, there's some, so I magnified this part. You can see there's a little bit of difference, well, significant difference. But again, in wind-resistant design, we're more concerned at the higher amplitudes. And here, the difference is not as significant as in these lower amplitudes. So yes. And just one last thing about higher order modes. Here you can see, so this is just a one DOF system and then 2 DOF system, mode 1 and mode 2. You can see the shapes again are similar to the 1 DOF system, which suggests 1 DOF representation is also valid for higher order modes. But here, an interesting result is mode 1 damping, mode 2 damping is higher than mode 1 damping only at, let's say, this amplitude range. But at the higher amplitude ranges, mode 1 damping is higher than mode 2. So it depends on what amplitude range you're looking at to say which which mode has higher damping. Yeah, that's the end of chapter 3. I'll just skip this summary. Chapter 4. So now I move on to looking at actual physical structures using what we've learned so far. So here I'm talking about experimental models where we introduce stick-slip components. So for example, I have a laboratory scale experiment. I have two, by the way, to present here. Here, the objective is to observe stick-slip damping after a secondary component is introduced. But again, one important consideration is it's difficult to control the trigger displacement, because again, it's difficult to control the friction forces and more particularly the normal forces. So actually, I used different trial materials at first. I ended up with one, and that's what I'll present here. And I should also mention that I did some ambient vibration measurements, but they resulted in low signal to noise ratios and therefore artificially high damping. So I'm not going to talk about ambient vibration measurements here. This is the laboratory scale model that I used. It's all steel. All the connections are fully welded. So it's basically it acts like a 1 degree of freedom model in one direction within a certain frequency range. It has 4 columns and then 1 mass plate. And then here's just a photo of the impact hammer I used to create an impulsive load and cause free vibration. And well, anyway, the measurement settings and measurement tools I used. I had a sampling rate of approximately 100 times the first mode frequency and about less than 10 minutes of free vibration recording. And this is the stick slipping component I use. Basically, you can imagine this. So this is a brush. It has a large number of hairs, brush hairs, and then of course it's difficult to establish the. We can estimate some of the parameters, but in fact it's difficult to count the number of essentially stick slip components. So I introduced that into the system, attached that into this relatively rigid attachment. And so under the mass plate, it caused some friction. And after recording free vibration data, I applied the band pass filter with a wide bandwidth so that we do not affect the damping results. But the goal is just to filter out higher modes. And then I use least squares approximation for every 2 cycles of the free vibration response using a 1D model with 4 parameters. And then I evaluated error, and results with error above 0.1% are rejected to reduce the scatter. And these are the results. So I have a basic model here. You can see very low damping. Unfortunately, the results had high errors at lower amplitudes, so those were rejected. And there's still some scatter here. And then model with 6 components here, you can see a seemingly increase of damping with amplitude, seemingly constant part, and here seemingly decreasing part again. But because we have these measurements, we can establish a baseline damping and assume it to be around 0.06%. But here you can see that starting around this amplitude range, damping appears to start to increase. And I think it's because a little bit of material nonlinearity is already starting to occur. So if in terms of tip drift ratio, it's a very high tip drift ratio already. Much higher than, let's say, building response under 500-year return periods. And this is the selected stick slip model. It's basically just that one model I showed you earlier. So using the information of baseline damping from these results, we can fit this. But you can see here, the model only fits, only shows constant damping over 1 order of magnitude, but the data shows 2 orders of magnitude of practically constant damping. I think one reason for this is that, again, the seemingly increasing baseline damping already here does the difference. But also it could be that different model could be used to describe, to extend this constant damping further. But yeah, I wanted to emphasize that because we have measurements of the base, we were able to establish baseline damping values, we arrived at this model. If we didn't have that baseline measurement, we might assume baseline damping to be around 1%. So we would have a different model. So it's quite important to have done measurements of the basic model. This is another experimental model. I didn't do the experiments myself, but I just got the data. At first, they had very different objective, but essentially it's the same thing as the previous example. I have a basic steel structure, although this is not fully welded. And then they introduced non-structural walls. So let's say on 2 sides in the direction of in one direction. So we're interested in that mode. So again, we're interested to see if the addition of the wall contributed damping to the system and if stick slip theory could characterize it that way. Again, it's essentially the same methodology, except we use a higher error tolerance. And these are the results. Again, we can establish baseline damping. It's around 0.3% this time. And here you can see the damping due to the non-structural wall is decreasing, increasing, and so on. So it's, but in fact, we can fit one of the models I derived earlier to that. It's not a perfect fit, but with some adjustments, of course, we can still fit. And I think in terms of properties, it's comparable. So I mean, it can reflect actual conditions. So that's for experimental buildings. Now, last major chapter, I'll talk about, let's say, applications to full-scale buildings. So the last one was about experimental buildings. Key considerations, again, stick-slip damping suggests increasing damping and then decreasing damping with amplitude, such as in this case as well, full-scale measurement. And then there could be damage to secondary elements, which would increase damping again at the very high amplitude. But there's no sufficient evidence yet of such, and this is not considered in wind-resistant design, so we will not consider that. And there's a proposal to use higher wind load factors to account for uncertainty, or to use lower damping values to account for uncertainty. But these are to account for uncertainty, so these should be considered on top of the consideration of amplitude dependency. With that, this is the illustration of the framework that I thought of. Essentially, we assume that damping increases. Maybe it will stay constant for a little while, the maximum value, and then decrease. So one simple approach to pursue this framework is, let's say if we have established baseline damping, we can just simply assume that as the damping ratio for, let's say, safety design, or at the very high amplitudes. Of course, another simple approach is if we have measurements, let's say up to here, and then we don't have any more measurements, we can say that damping will start to decrease from that part. So of course, following stick-slip damping theory. So that's one example is in current models actually. So there's a baseline damping value already. We can use that for safety design purposes. These are for different models. You can see there's a little bit of differences. Let's say for 200-meter high building in the damping estimates, but I think it's because these are for buildings in Italy, for buildings in Japan, and then these are for buildings in the US and the UK. So just to illustrate the second approach, another example is, let's say we can take an existing predictor model, for example this for steel buildings in Japan, and then just modify it according to stick-slip damping theory. But we have to use the measurement, the equation based directly from the measurements, which is this. And so I reformulated it. But based on these parameters of reformulation, we can establish baseline damping and so on, all the other parameters that describe our model. And then this is the final model. As you can see, it's quite simple enough. And for example, for different buildings, this is what it would look like. So of course it changes, the general damping level changes with height, but they all decrease in a similar way. Approach number 3 is curve fitting of a stick-slip model. Curve fitting itself, I've tried it. It takes a long time, very complicated because there's a lot of unknowns. But alternatively, we can just select from a database of stick-slip damping models, so such as that I developed in chapter 3. We just need to identify certain parameters and so on. I'll go very quickly. This is, I showed you this earlier, data for a 200-meter high steel building in Japan. At first I established the amplitudes of concern, let's say amplitude at a 1-year return period, which is corresponding to habitability design. Let's say 50-year return period, which is corresponding to safety design, and even 500-year return period, and so on. Just using the available information from AIJ recommendations and from the measurements. I tried to fit some models. The initial models I used are showing certain baseline damping. From the data, it does not show a very good fit. I just adjusted the baseline damping and I can get a better fit. So this is a multiple stick-slip component model. But in fact, I can also fit a one stick-slip component model. And here you can see it's a sufficient fit. Here is comparing the two selected models I used. And then in terms, so here, this corresponds actually to 1-year return period response, approximately. So we're interested in, let's say, 50-year return period response. It's at higher amplitudes. The data, of course, does not have that, but our models can, based on this curve fitting, can predict. So I compared some of those damping estimates for habitability design and safety design, and compared the increase in wind loads as well. And basically, the conclusion I have is the wind loads could increase by as high as 20% when that decrease in damping is considered. And so, if we account for both damping uncertainty and damping decrease with amplitude, the increase in wind loads would be around 30% higher if the damping value used compared to using current model. So very last one, full-scale tall building in Hong Kong. I did the same analysis. Essentially, somebody did frequency domain analysis. They arrived at these results. Took a look at, let's say, at the first two modes. I used the same methodology, except I used multi-mode random decrement technique because I have closely spaced modes. And these are the results. Effectively, the amplitude levels are very low, so 10 to the minus 6. Whereas, for example, 1 year return period response is around 10 to the minus 4. So, and then at the same time, Professor Tamura talked about critical tip drift ratio around 10 to the minus 5, 10 to the minus 4, where the damping starts decreasing with amplitude. So it's even much lower than those levels. So in a sense, we could assume that these are baseline values, baseline damping values. So let's say for mode 1, we can say baseline damping value around 0.3%, mode 2, baseline damping value around 0.4%. So these could be used, let's say, for safety design, but of course they could also be used for habitability design, but I think they can be conservative. Basically, the conclusion here is without the measurements at higher amplitudes, it's difficult to establish the amplitude dependency. We can only establish the non-amplitude dependent component or baseline damping. So yes, that's all. Just a closing remark. So I believe I've met the main objective of the study of illustrating whether or not stick-slip mechanism can describe damping in buildings. So I studied stick-slip theory and applied the findings to actual physical structures with stick-slip components. I also briefly discussed a possible framework for new damping predictor models based on stick-slip mechanism. And well, I hope that at the very least, the findings in this study are considered in discussions that aim to improve the practice of wind-resistant building design. That's all. Thank you. Thank you very much.
Thank you very much. Now, I'd like to open for discussion. And are there any comments or questions from the audience? Any questions or any comments?
Thank you for this nice presentation. I'm a bit surprised because you talk about damping depending on the motion, but in fact, you're just playing with a bilinear stiffness or multilinear stiffness.
Mm-hmm.
You are changing your structural stiffness, aren't you? In the equation of motion, the basic equation you showed the beginning. Maybe the first slide. With your age mentioned. So the equation in the bottom, you just change the K, the value of the total K. So it's a stiffness.
Yes.
You don't change the CV, which is the viscous damping term.
Yes, I don't.
So that's why in the data and the data from Professor Tamura, you see the decreasing of the frequency. Because this is a nonlinear softening effect. When the building is bending, it loses a certain amount of stiffness. So you have the frequency decreasing, and if you divide the decreasing frequency, if you divide CB, which
slide. I'll just go to another.
It's just in terms of nomenclature of the
Yeah. 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 I hope. Well, thanks for the question. I hope I understood it well. But let's say, actually, I found I didn't show it here, but I found that it would seem like after the slipping starts to occur, let's say here, there's just a sudden change in stiffness. But actually, what's happening, I found, is that so up to this point, for example, the stiffness is constant. But after that point, where there's a sudden change in the total stiffness, what's actually happening is it's the second, well, I call it second stiffness here, that that governs the nature of the decrease of frequency. And so and then it's actually a gradual decrease of that second stiffness, which leads to that gradual decrease of frequency as well. In fact, I don't have it here, but and I didn't want to discuss frequency amplitude dependency because it's not the focus. But in an earlier version of this slide, yeah, maybe I don't have it here, but in an earlier version of that slide, this same modeling can also account for the decreasing frequency with amplitude.
I think you're right. It's just maybe the reason of this decrease of damping is due to the softening of the building. And this wasn't clear in your group. This is not clear for me at least.
Yeah, actually, it's yeah. The way I see it also is it's a matter of geometry. So let's say we're looking at this. Let's say general shape or using applied to this force displacement. Basically, from this point, the damping increases with amplitude, but up to around 2 times this level, that's when the damping decreases. So there's sort of an increase first before that decrease as well. So
maybe we can discuss
yeah,
the equation and
yes, sure. That would be interesting. Thank you very much.
Thank you very much. Have any questions? I have one question. Your achievement is especially for the theoretical treatment is applying for the free decaying oscillation situation. I'd like to ask you some perspectives or comments for the application of this model to the random vibration situation.
So yes. One thing I think about it is, so random vibration, of course, let's say we have, let's say, do you mean like wind loads or earthquake loads? So of course, if it's under earthquake loads, it's a different, but let's say under random vibrations, let's say almost similar to white noise excitation. I think what happens there is the main frequencies of the system would be excited, and therefore, and then some techniques, for example, that's what random decrement technique can do. Other, even some frequency domain techniques can do that. It can isolate the modal response from the noise. So in that sense, in fact, let's say the random decrement technique results in something similar to the free decay case, but I mean the random decrement signature. So those kinds of methods can isolate what is effectively noise compared from the modal response itself, let's say in the frequency domain.
But your model is
Yep.
no more linear.
Yes, yes.
How
Yeah.
do you predict the responses?
Yeah. Actually, so I looked at let's say free vibration data, but essentially approximately one cycle would correspond to the damping evaluated there would correspond to the damping under cyclic motion as well. So let's say if it's rather steady state, I think even random vibration, it would cause effectively cyclic motion in the system, which sticks the component. And therefore, you just need to establish let's say the amplitude of that cyclic motion in that mode, and then you can get the damping as well. But if it's unsteady, let's say excitation, so yeah, that might have an effect. I did not consider that part yet.
Are there any questions? Okay, thank you very much. 田村先生からコメントを
So I think this study is very good, have a good quality, and I deserve to the PhD. He did the TBU in 2005 as a short-time fellowship, and around that time I found some new kind of concept, especially the critical tip-drift ratio, where the damping reaches its maximum, then decrease, but nobody, not so much supported by other people. But he made some study supporting this concept, especially the stick-shift model is not so, of course, not so new, but only the conceptual or qualitative study can be made, but such a quantitative study has not been made. And this study supported kind of new findings, critical ratio. So I'm very happy